Okay, here in this research, we solved a 676-bit discrete logarithm problem in GX326M. In this talk, we talk about why and how to solve this problem. Okay, this is an outline of our talk. Motivation. We explain our motivation and the function field, which is most important algorithm in this problem. We explain our experiment, and finally, we conclude our talk. The key point in our talk is these improvements, namely correlation and gear action. Okay, here we talk about our motivation. And based on pairings, many novel cryptographic protocols have been constructed successfully, such as ID-based encryption and keyword searchable encryption, and so on and so on. Moreover, pairing-based crypto system can be implemented efficiently. The ETT pairing on supersingular caps over GX32N is one of the most efficient pairings. Because of its application and efficiency, pairing-based cryptography becomes one of the main topics in cryptography. Along with increasing computational speed, one may ask whether this crypto system is still secure. Okay, the security of pairing-based crypto systems is based on the discrete logarithm problem in two groups. And one is an elliptic curve, and the other is a final field. In the case of the ETT pairing over GX32N, the security bases are the discrete logarithm problem on supersingular curves over GX32N on this side, and the discrete logarithm problem over final field GX32N on this side. And our target in this research is on this side, the discrete logarithm problem over GX326M. And the function field is the most efficient algorithm to solve this problem. And so we implement this. And here we explain an overview of the function field. The function field has 4 steps: a polynomial selection, a collection of relations, linear algebra, and individual logarithm. In polynomial selection, we select bivalent polynomial h as definition polynomial of the function field, and the reducible polynomial f, which is a definition polynomial of final field, and compute m such that xm is congruent to 0 modulo f. And then choose the parameter, the smoothness bound b, and compute rational factor base br and algebraic factor base ba, where a rational factor base is a set of irreducible polynomials of degree not larger than the b, and algebraic factor base is a set of small prime divisors, as this. In correction of relation step, correct many relations between logarithm factor base, as this. In linear algebra step, we solve this linear equation, where M is a sparse and large matrix constructed by relations, as this, and V is a vector constructed by logarithm factor base, as this. By solving this linear equation, we obtain logarithm factor base. And finally, in individual logarithm step, we compute logarithm target element from logarithm factor base. Okay, and here we explain our implementation choice. In polynomial section, we chose a variant of functional field sieve proposed by Joan Redsier in 2006 and implemented polynomial sieve per Ranchos method, a special queue descent for each steps. Collection relations and linear algebra needs many computations. And so to decrease the number of computation, we deal with some improvements, correlation and interaction described later. Okay, here we explain our experiment and computational result. And these pictures are our computational environments. 12 rack-mounted servers. Each server has Quad-Quad and 6 tower servers. Each servers have their CPUs or Quad-Quad. In total, we used 18 Xeon servers and 96 cores. Each server is connected by gigabit Ethernet. We use some OSs, FreeBSD and Fedora, and so on, and compiled by GCC with some libraries, GMP, MPI, and so on. Okay, here we talk about our computational result of solving the discrete logarithm problem over GX326 times 71, which has 676-bit cardinality. At first, we construct GX326 as this, and to represent an element in polynomial ring over GX326, we define map phi as this. Map psi as this. Sorry. And in polynomial section, we fix a bivariate polynomial h as y26 plus x. And this is to compute efficiently in correction relation step. And find irreducible polynomial f whose all coefficients are in GX3. And this restriction comes from a interaction described later. And then compute m. By an easy computation, we obtain such f and m as this. And then construct GX326 times 71 as an extension field over GX326 of degree 71. Okay, with the generator of this group, gamma as this, and target element pi x as this, we solve logarithm pi x in basis gamma. We set the smoothness bound b equal to, this is because limitation of our computational environment and our implementation. Then the number of rational factor base and algebraic factor base are about 250,000. And so the number of recurrent relations are about 500,000. This is a bit too many. And to decrease this, we dealt with the interaction and correlations. Okay, here we required about 500,000 relations. By correlation, we obtain about 0.13 million relations, and that is 1 quotable. And so we should search about 0.4 million relations. Furthermore, by interaction, this compressed to 1/6, and so we should search about only 66,000 relations. Okay, here we talk about correlation and interaction. At first, correlation. Correlation is relation obtained without some computation, such as sieving. If h is factorized to degree 1 polynomial modulo p as this, And then we obtain a free relation as this. In many cases of the function field, the number of free relations is about that of BA over D, where D is degree of H in Y. However, in very small character case, as our case, there are more free relations we can obtain. For example, in our case, we chose H as y to 6 plus x. And then y to 6 plus x is factorized to as this for most of P. And so the number of relations is about that of BA over 2. And that is 3 times more relations we can obtain. And next, gear action. To use gear action, we select an irreducible polynomial f whose all coefficients are index 3 and construct final field as this. And then for map phi, which maps to 3 to nth power, x is fixed modulo f. And so an element in rational factor base P, then P prime which is phi of P is also in rational factor base, but not equal to P. And therefore, logarithm of P prime is multiplied by 3 to nth of logarithm P. And this fact enables to compress two terms, namely logarithm P and logarithm P prime, to one terms in matrix in linear algebra step. By applying phi iteratively, 6 terms can be compressed to one term in the matrix for most of P. Furthermore, gear action can be also used for algebraic factor base. Therefore, the number of recurrent relations are reduced to 1 over 6, and computational time in linear algebra is reduced to 1 over 36. And because of complexity of linear algebra step is of quadratic order. Okay, back to experiment. We should obtain about 66,000 relations, and that is 1 over 8 of original 1. By 18 days computation, we obtain 66,000 relations, and we have enough relation to compute linear algebra step. Okay, here we explain about computation of linear algebra step. In linear algebra step, we solve this linear equation by Paralanchus method. In computation, we remove small prime factors from this modulus and divide it to 4 moduli as this. There all moduli are fairly coprime. And in Paralanchus method, we divide the matrix by horizontal and vertical as this. And more, work for all moduli in parallel. And then we solve modulo n by Chandler-Mellon theorem. By about 12 hours computation, we solve this linear equation and obtain logarithm factor base. And finally, we computed logarithm of pi x in basis gamma modulo n, where n has 548 page size. This was computed by special Q descent. This took about 40 days. this is much longer than our forecast. This is because the galaxy and correlations cannot accelerate the individual logarithm step in general. And logarithm modulo small prime factors are computed by Polar's law method. And finally, we obtain logarithm of pi x in basis gamma as this. And completely solve discrete logarithm problem over GX326 times 71. Okay, this table shows the current record for solving discrete logarithm problem over various finite fields. And this is our work. Our work is the largest bit size, even though each experiment uses different algorithms, number field sieve, and function field sieve. There are many kind of finite fields, such as prime fields, binary fields, and so on. However, there are no specialized experiments over field related to the security of pairing-based crypto systems, such as GF224N, GFP210, and GFP212. And so, we should experiment and evaluate the difficulty of discrete logarithm problem over such fields. Okay, conclusion. In this research, we succeeded in solving the discrete logarithm problem over GX326 times 71, which has 676-bit cardinality.